In this mini lecture for Chapter 19, we are going to learn about a really useful reaction for organic synthesis. And it is a reaction that will bring to fore all that we learned about with respect to oxidation and reduction. So the reaction we're talking about is reducing multiple bonds, be they alkenes, alkynes, or carbonyls, with hydrogen gas. So let's get started. Reducing agents, you will see, invariably in organic chemistry, invariably add hydrogen. So as I go from the ketone on the left to the alcohol shown, you can see I've added a red hydrogen. Okay, that's a reduction. If I do it again, if I add two hydrogens to my carbonyl and somehow or other get rid of the oxygen, that's still a reduction. So I'm adding hydrogens. Going from an alkene to an alkane, adding hydrogens, that's a reduction. Going from an alkyne to either the E or the Z alkene, and then even further, all the way down to the alkane, you got it, it's a reduction. So what you want to note, and what will become quite evident in the next slide, is that in going from left to right in all of these examples, we are going from a higher, more positive oxidation state to a lower, more negative oxidation state, hence, again, a reduction. So let's just do a little math here. I've got an oxidation state of +2 here because 0, 0, and -2. That means the carbon on my ketone must be +2. And now I have 0, 0, +1, -1. Those two cancel each other out. So my oxidation state is going from +2, a more highly oxidized carbon, to 0, a less highly oxidized or more reduced carbon. And of course what you should do is kind of go through the math for all of these and convince yourself that, yeah, in fact, these are the changes in oxidation state. Just to kind of make things really clear, what we're talking about is the change in oxidation states of the affected carbons. So I'm highlighting the affected carbons with the little yellow highlighter. Those are the ones you want to calculate the oxidation states for and convince yourself that, yes, all of these reactions are reductions. That said, let's get out of here and go to the next slide. Please let me go to the next slide. There we go. We're going to focus on the reduction of alkenes to alkanes. In fact, all of this mini lecture has to do with catalytic hydrogenation. That is the reaction that we're going to be looking at. Adding H2 gas in the presence of a catalyst. So catalytic hydrogenation of alkenes just adds hydrogen to a double or triple bond. Now, that should be fishy because I've tried to hammer it home all the time. You know, electrophiles react with nucleophiles and vice versa. And hydrogen gas is not either one of those. So it's special, and it doesn't do anything except explode unless you have a transition metal catalyst. Okay, basically hydrogen is pretty much an inert gas, except it likes to combust and it likes to react with transition metal catalysts. So this is a funny reaction in that we really don't get to push arrows at all. There's not really a mechanism that we can look at least not in this class. So instead we focus on kind of a macro, micro, physical picture of what's going on. That means we have to think about the catalyst and what it's made of. So the catalyst has two parts. One is the transition metal. Typically, you guys are going to see palladium, platinum, or nickel. So those are nice, right in the middle of the periodic table transition metals. They're generally kind of pricey, although nickel is not so pricey. But because they're kind of pricey and we don't need much of the catalyst, the other part of our catalyst is some junk that's cheap upon which we can coat our pricey metal. That's called the support. So here's a nice little cartoon that shows what we're trying to convey. You see the blue dots here are my palladium atoms. And I really just need a monoatomic layer of palladium atoms upon which the reaction can take place. But that, of course, is not feasible. So I have junky, cheap support layer. This stuff, like calcium carbonate's basically chalk. Carbon is graphite. So you have particles of chalk or barium sulfate or carbon upon which you layer a very, 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 very thin coating of your transition metal atoms. And then what happens, and this is as close to a mechanism as you're going to get in this class, your alkyne or your alkene will kind of settle onto the surface of the transition metal, as will, I don't think you can really see this, but there's a good picture in your book too, as will the hydrogen. The hydrogen coats the surface, and then the alkyne or alkene coats the surface. And basically they interact so that the hydrogen is delivered from the same side of the alkene or the alkyne, and the reduction takes place. So it's kind of magic because it's no electrophile, no nucleophile, and we don't show electron movement. You just get reduction of your alkene. So here is the synthesis of Propecia, where we just took out that double bond right there and added 2 hydrogens. And I'm not going to take a guess on whether both hydrogens are up or both hydrogens are down, but they will definitely be added to the same side of the alkene. There is the alkene, then alkene is gone. A reduction. What about alkynes? Well, alkynes, as I suggested previously, well, they'll undergo an addition of hydrogen, add H2, and you get an alkene. What I've shown here is clearly a Z-alkene. We've already learned that if we want to make the E-alkene, we use the dissolving metal reduction, and that gives us the E-alkene. So now we're learning a way to control the stereochemistry in reducing an alkene down to an alkyne down to an alkene by the addition of hydrogen and catalyst. But wait. What we're looking at is going from oxidation states of 0 to oxidation states of -1. But the problem is, as we just saw, alkenes can easily be reduced in the presence of hydrogen gas and a catalyst to go all the way down to the alkane. So we need to be able to figure out a way to somehow or other stop the alkene from being further reduced down to the alkane. This is basically controlling the reactivity of the process. How do we do that? Simple can be, just add some poison. So if I poison the catalyst and reduce its activity, and this is actually going into organometallic chemistry, which again is kind of beyond the scope of this class, but you can add things that will kind of, I'm just going to say clog the pores of your catalyst, which is a gross overstatement, but you kind of get the picture. It reduces the activity of the catalyst and keeps it from over-reducing. So now instead of 2 parts of the catalyst, there's 3. We have the transition metal, we have the support, but now we also add something like lead or the molecule quinoline, which basically makes the catalyst not work so well. This particular mixture is called Lindlar's catalyst, but I do want you to remember that there are the 3 parts, the usual catalyst, the usual support, plus some poison. Now, how does it work? Well, if I just take an alkyne, throw it in with hydrogen and a transition metal on a support, I'm going to get the alkane. That's all there is to it. We can't really control the addition of hydrogen gas. It will over-reduce all the way down to the alkane. But if I use Lindlar's catalyst and add quinoline, I can put tons and tons of hydrogen gas through that system, and the reaction will stop at the alkene. And again, note that because of the nature of how this works, and the fact that it's starting from a surface where my two little hydrogens are going to be added from the same side, I get the Z-alkene. So there you go. That's how you hydrogenate alkynes and alkenes. Now what about other multiple bonds like C double bond O or carbon-nitrogen triple bonds? Can they be reduced this way? And yes, they absolutely can. It's a nice reaction, but it all depends on the reactivity of the functional group. And some of these functional groups are relatively slow to react, which is good because then you can control the outcome of your reaction. So you should refer to table 19.3 to see what kind of things you can vary if you want to reduce, say, an alkene and not an amide. All right, it all works because these guys have pi orbitals and like to interact with the hydrogen on the palladium surface. But if you really want to control selectivity of reducing a carbonyl, for example, to an alcohol, you might want to take advantage of the fact that it's an electrophile, and you can add a nucleophile like H-, but we will learn about that when we revisit chapter 19 later. Okay, so I'm kind of hinting at selectivity. If hydrogen gas likes to react with just about anything with multiple bonds, how can you control it? And this is actually not really out of the question. If you look at the star material on the left, you can see we have two alkenes, one monosubstituted, one trisubstituted. They look fairly similar, but think like a molecule, think like a model set. The one at the tail, the monosubstituted one, is actually a lot easier to get to, a lot more accessible, a lot less crowded. So you can control this reaction. You can control the reactivity simply by sterics. Just keep the conditions mild. Watch the reaction. This will get reduced first, and then you can work up the reaction and you're good to go. How about going from the amide on the left to the saturated amide on the right? In other words, we are taking out, again, that double bond. Well, this is what we saw earlier. This was the synthesis of Propecia, and basically, because the amide is pretty unreactive, even at, these are harsh enough conditions. I mean, that's a long time, and it's an elevated temperature, but I got rid of the alkene and not the amide, or for that matter, the acid, both of which could be reduced. So pretty easy to control just on the basis of reactivity. So finally, we just need to wrap up this catalytic hydrogenation thing with a little tale about the fact that Ole decided he wanted to be buried at sea. And the reason why is because he always said that Lena always said that she wanted to dance on his grave. What can I say? It's an Ole and Lena joke. All right, see you guys in class.